In the last video, we saw how references can help multiple parts of our code work with the same data. References are a powerful tool, and you'll see them in most C++ code bases, but they do have a few limitations. And in this video, we're going to discuss those limitations and talk about a new tool, pointers, which relax some of those rules. First, when you create a reference, you have to tell it what it's going to point to right away. You're not allowed to have a reference that just sits there not pointing at anything. We've got to tell it right away, you point to this piece of data over here. And the second big limitation is that references can't change what they're pointing to. Once you tell a reference that it's pointing to one piece of data, you would need a new reference to point to some other piece of data inside of your code. And there's no way to just go ahead and do an in-place, swap of saying this reference now points to this second other piece of data. So pointers introduce two new concepts into the language that help us tackle these limitations of references directly. And these are mutability and nullability. And of these, mutability is probably the easier to understand. The mutability of pointers just means that we can change what data a pointer is pointing to. So looking back to our diagrams of these reference relationships, with a reference, we were stuck. We could point to D1, but then that was all we could ever point to for the lifetime of the reference. And instead, if we had a pointer as the type of our handle, we can get rid of this existing relationship and replace it with a new relationship that points to D2. And this can be done dynamically at runtime as many times as you want with the same pointer in C++. We can go around creating and destroying data and swapping out what P points to back and forth however we want, as many times as we want. And so we call that mutability. And the other new concept, nullability, means that we can have pointers that don't point to anything at all. And we call a pointer that doesn't actually point to anything a null pointer. Null is to pointers like 0 is to counting. And just like dividing by 0 can cause problems in math, null pointers can give us trouble in our code if we're not careful with them. Dereferencing a pointer, or asking what it's pointing to, will cause undefined behavior if that pointer is null. The compiler will follow this relationship to find the data that P is pointing to and won't find anything, and so it won't know what to give us back. Most common instances of using null pointers will cause what's called a Seg Fault Error and crash your program. So if you run your code and see the message segmentation fault core dumped, then there is probably a part of your code that is using a null pointer. One more important thing to consider about both the mutability and nullability of pointers is that the data being pointed to doesn't know when these relationships change. This is important because if your data is an object that needs to clean up resources before it's destroyed, you need to remember to trigger that cleanup before you lose all of your pointers to that data. The object itself won't know when you stop pointing to it, so it can't handle that automatically for you. Now let's take a look at the syntax for using pointers in our code, and we'll start with declaring pointer variables. Similar to references, we're going to tell the compiler we want a variable to be a pointer by adding a character to the type name, and in this case, that character will be the asterisk, or the star character. So here, we have the variable myPointer, and we know that myPointer is going to be of type pointer to an int. And note that this time we've left off the initializer. Because pointers are allowed to be null, there's no requirement that we initialize it to begin with. When we were working with references, we didn't need any special syntax for creating and following the reference relationships. Pointers, however, require a few extra characters of syntax for those operations. Let's start with creating a new pointer relationship. We can do this by using the address of operator, which is an ampersand put before the name of a variable. The right side of this statement uses the address of operator to create a pointer that points to real variable, and then we assign that newly created pointer to our pointer variable on the left. And we'll also need a little bit of extra syntax to follow these pointer relationships. So instead of just being able to use a pointer variable name like the regular variable name as we did with references, we're going to have to use something called the indirection operator to follow the pointer reference before we operate on it. And the indirection operator is this asterisk in front of the pointer variable name. So on the left-hand side of this statement, we dereference the pointer variable, and that gets us to the underlying real variable. And then we use the combined arithmetic and assignment operator plus equals to add 5 to that underlying variable. And again, to read the variable, we're going to have to use the indirection operator again to follow that pointer relationship maintained by pointer variable to the underlying data so that we can read it and print it out. And so when all of this example code runs, we'll print out the value 15. Similarly, if the underlying data is an object, we need to dereference the pointer before accessing members. And so you could write code like this, where you first use the indirection operator to dereference my object pointer, and then on the result of that, call the my function member. But there's actually a shortcut syntax for this. This arrow here is a combination of the indirection and member access operators. And thus, these two examples are exactly equivalent to each other. Both of them take an object to a pointer, dereference it, and then call a member function on that dereferenced object. This second way just gives us a much cleaner syntax for doing all those steps, and so this is what is used in most code. When we want to modify a pointer relationship and make that pointer point to some other piece of data, we can just use the address of operator again on this new piece of data and use the assignment operator to replace the relationship. So this ampersand will create a new pointer to another int, and then the assignment operator will replace whatever the pointer relationship that my pointer currently has with the pointer relationship that points to another int. And the last bit of normal syntax has to do with the nullability of pointers. C++ gives us a special constant so that we can do useful work with the concept of a null pointer. This constant is called null pointer, or sometimes people will pronounce it null putter. And to nullify a pointer, we can just assign the value of that null pointer constant to our variable, like this. And of course, because accidentally using a null pointer is so dangerous, we need a way to tell if a pointer is null, and we can do this by comparing our pointer against that null pointer constant. You can work with pointers to just about anything in C++, and when all of these different syntaxes start stacking up, things can get a little dense with special characters. So let's take a minute to go over some common situations you might see. And this is where we're going to get into some of the wackier syntax you'll see in C++. So let's say you want to make a pointer to a member of a class or a struct. You'll need to scope the pointer declaration with the name of the class, and this will affect the subsequent operations you use. So here we want to take a pointer to an int, but that int is a member of my type. So we'll take the address of my type : member name, where member name is some integer variable inside of my type. Then when we declare a new instance of my type, in this case we'll call it my instance, to actually get to the member name member of my instance, we say my instance dot star pointer to member. It's definitely a little wacky. You won't see this kind of thing in most regular code, but it's important to be able to just break it down and wrap your head around what it's doing. At the end of the day, pointer to member is still just a pointer to an integer. In this case, the only thing we're adding is that that integer is within the class myType. And while this access syntax looks wacky, we can break it down by saying we're using the indirection operator to dereference pointer to member. And that's going to give us the member name member. Well, when we have an instance and we want to get to its member, we use the instance name dot the member name. And since this right-hand side dereferenced to the member name, we just say my instance dot member name. So the logic is there if you take it step by step, but when you squint at it from far away, it definitely looks a little weird. Something that you might actually see a little more often are pointers to functions. This syntax looks a lot like the declaration of a function, but we add parentheses and an asterisk to tell the compiler that it's actually a pointer variable. So here we're declaring a pointer variable called pointer to function. And the things that this pointer to function can point to are functions. Specifically functions that take in two ints, we call them arg1 and arg2, and then return an int. And so we can actually take a pointer to a function f that follows that signature, takes in two ints and returns an int, and assign that pointer to function. And now whenever we dereference and call pointer to function, we'll actually be calling f. And again, if we want to only work with functions that are member functions of some type, we can add the type name to the declaration in a similar way to when we were working with regular variables. And finally, here's one more pattern that you'll see, especially when you're working with old C APIs or libraries. Pointers to void. Void pointers are special because any other type of pointer can be cast to and from a void pointer. An example of a common use of this idiom is when you want a callback for an event to include some custom data structure that the library knows nothing about. The library can happily pass around the pointer to void as it needs to, and when it hands it back to your code, you can cast it back to the real type which only you know. There are a lot of safety and security concerns with this pattern though, because the compiler has no way to check for you if you're casting the correct data to the right type. Pointers are an important mechanism that make all of your favorite abstracted high-level programming languages possible. With that said, we've come a long way from the days when C was the most abstract language available. There are a lot of tools for handling things that might have previously been done with pointers. These alternatives are generally easier to use and safer, so they should be preferred. We'll dive into some of these in future lessons.